A neutron leaves the shelter of an atomic nucleus and drifts into empty space. Nothing about it appears unusual. It has no electric charge, no visible surface, and no sign that anything is about to change. Yet somewhere inside that tiny particle, a quiet clock has already begun. In a little more than 10 minutes, on average, one of its quarks may change its identity, and the neutron will no longer exist. It will become a proton, an electron, and a nearly weightless antineutrino, moving away into the dark. The same neutron, when held inside a stable nucleus, can remain unchanged for longer than Earth has existed. Alone, it is temporary. Bound to other particles, it can endure. If calm explorations of physics help make the night feel a little wider, a like, a subscription, or a share helps this channel continue. It would also be lovely to know where this is playing, and what time it is there, whether the room is still awake or already beginning to fade into sleep. The lights can be lowered now. A fan may be left turning softly in the background. There is no need to follow every number or remember every name. A comfortable position is enough. The story can move at its own pace while the body grows still, and the edges of the room become less distinct. The neutron begins in a place that seems familiar, the small diagram of an atom once drawn on a classroom board. At its center sit protons and neutrons, presented as simple pieces with simple roles. But the neutron is not a smooth, silent sphere. Beneath its neutral surface is a restless interior of quarks, gluons, motion, and stored energy. That hidden interior is where the story truly begins. The first picture of a neutron usually arrives in a classroom. A circle is drawn for the nucleus. Smaller circles are placed around it, and 3 names are written beside the diagram: proton, neutron, electron. The proton carries positive charge. The electron carries negative charge. The neutron carries none. In that simple arrangement, the neutron appears to be the quietest piece, a small, neutral object, resting among the protons, while chemistry unfolds farther out. The picture is useful. It explains why atoms have mass, why elements differ from one another, and why changing the number of protons changes the identity of an element. It also leaves almost everything important hidden. The history begins with particles that once seemed final. The electron is identified near the end of the 19th century, when J.J. Thomson studies rays moving through evacuated glass tubes and finds that they are deflected by electric and magnetic fields. Whatever carries those rays is smaller than an atom and bears negative charge. The atom, long treated as indivisible, has opened. A little more than 2 decades later, Ernest Rutherford shows that positive charge is concentrated in a tiny central region. The nucleus is not a vague cloud spread through the atom. It is compact, dense, and surrounded by mostly empty space. The proton soon takes its place as the positive particle within that center. One problem remains. Atomic nuclei often weigh more than their known protons can explain. Their electric charge gives one number, while their mass gives another. Something neutral must be present, but for years that missing component is difficult to isolate. In 1932, James Chadwick directs alpha particles at beryllium and studies the unusual radiation that comes away. The radiation carries no electric charge, yet it can knock protons from materials rich in hydrogen. Its behavior makes sense only if it consists of particles with nearly the same mass as protons and no net charge. The neutron has entered physics. For a time, the new arrangement feels complete. Ordinary matter appears to rest on 3 particles. Electrons occupy the space around nuclei. Protons define the element. Neutrons add mass and help nuclei hold together. Stars, planets, dust, water, stone, and living cells can all be described as different arrangements of those 3 pieces. The picture is clean enough to remain in textbooks for generations. It is also temporary. During the middle decades of the 20th century, particle accelerators grow more powerful. Protons and other particles are sent into collisions at energies that do not occur in ordinary chemical reactions. The results are crowded. New particles appear, then more after them: pions, kaons, lambda particles, sigma particles, and short-lived resonances fill experimental records. Some decay almost as soon as they are produced. Others leave curved tracks in magnetic fields before changing into lighter forms. The list becomes so long that physicists begin speaking of a particle zoo. A zoo suggests variety without order, and that is close to how the field feels at first. Each new particle seems to require another name, another set of properties, another place in a growing catalog. Yet patterns begin to show through the confusion. Some particles share similar masses. Some differ mainly in electric charge. Some appear in families that behave as though they are variations of a smaller number of hidden structures. The neutron is no longer alone as a mystery. The proton, pion, kaon, and many other particles seem to belong to a deeper system. In 1964, Murray Gell-Mann and, independently, George Zweig proposed that many of these particles are not elementary. They are combinations of smaller constituents. Gell-Mann calls them quarks, borrowing the word from a line in James Joyce. The name sounds light, almost playful. The idea beneath it is exacting. A proton is built from 2 up quarks and 1 down quark. A neutron is built from 1 up quark and 2 down quarks. Many of the particles in the zoo can be organized as other combinations of quarks and antiquarks. The difference between a proton and a neutron is therefore small in description, but large in consequence. Replace 1 up quark with 1 down quark, and the total electric charge changes. An up quark carries positive 2/3 of the elementary charge. A down quark carries negative 1/3. In a proton, 2 up quarks and 1 down quark add to positive 1. In a neutron, 1 up quark and 2 down quarks add to 0. Neutrality is not emptiness, it is balance. This changes the way the neutron must be imagined. It is not a blank sphere with no charged structure. Positive and negative contributions exist inside it, arranged so that the total seen from far away is 0. The cancellation is exact at the level of overall charge, but the interior is not uniform. Later scattering experiments show that the neutron has an internal charge distribution and a measurable magnetic moment. Those properties would make little sense for a truly featureless neutral particle. They fit naturally once moving charged constituents are present. The quark proposal is not accepted at once. Some physicists treat quarks as a mathematical language rather than physical objects. A useful model does not automatically prove that its pieces exist in nature. The question remains open until experiments begin probing nucleons at much shorter distances. At the Stanford Linear Accelerator Center in the late 1960s, high-energy electrons are fired into protons. Electrons are chosen because they do not feel the strong nuclear force in the same way quarks do, making them clean probes of electric structure. If a proton were smooth, the electrons would scatter in a broad and predictable way. Some do. Others strike something much smaller and more concentrated, returning at sharp angles. The pattern resembles an earlier turning point in atomic physics. Rutherford once used alpha particles to reveal that an atom contains a tiny nucleus. Now electrons reveal that a proton contains compact, point-like components. The experiments do not show quarks as little photographs. No instrument can simply display one sitting still. What they show is structure at scales, where a smooth proton should have none. The components first receive the name partons because the experiments establish that there are parts before their full identity is settled. Over time, the partons match the quarks and gluons described by the developing theory of the strong interaction. The neutron, too, belongs to this same internal world. Its neutral exterior conceals charged quarks, fields, motion, and constant exchange. The old classroom circle has not become useless. It has become a distant outline. Even the phrase, 3 quarks requires care. The neutron is classified by 3 valence quarks, 1 up and 2 down, because those determine its main quantum numbers. But the space inside is not occupied by 3 fixed beads. Gluons carry the strong interaction between quarks. Their fields contain energy. Temporary quark and antiquark pairs appear within the changing quantum state. The neutron remains one particle, yet its interior is active at every moment. From a distance, none of this motion is visible. A neutron has a definite mass, a definite spin, and no net electric charge. It can move through space as a single object. It can settle into an atomic nucleus and remain there. It can also leave that nucleus and begin the slow path toward decay. The calm outer identity and the restless inner structure coexist without contradiction. Physics often works this way. Simple behavior at one scale can rise from activity that looks entirely different at another. The classroom diagram captures the scale where atoms perform chemistry. It does not capture the scale where nucleons are built. At the chemical scale, the neutron can be treated as a neutral unit of mass. At the deeper scale, it is a bound state governed by quantum chromodynamics, the theory describing quarks, gluons, and the strong interaction. Both descriptions are useful. They answer different questions. The question now moves inward. The quarks inside the neutron do not drift apart, even though they carry charge and move within a space smaller than the nucleus around them. No isolated quark has ever been observed. Every attempt to pull one free produces new composite particles instead. Something holds the neutron together with a grip unlike any familiar force. To understand why the neutron exists at all, attention must turn from the particles inside it to the field that refuses to let them go. The neutron's neutrality is exact only when the particle is viewed as a whole. Inside, the balance is uneven. One up quark carries positive charge. Two down quarks carry negative charge. Their total is zero, but zero does not mean the charges disappear. It means they are arranged so that, from far enough away, their effects cancel. Closer in, the pattern becomes more complicated. The up quark and down quark are the two lightest members of the quark family. 4 heavier flavors also exist: strange, charm, bottom, and top. Those heavier forms appear in short-lived particles and high-energy collisions. But ordinary protons and neutrons are built from up and down quarks. The word flavor is only a label. It marks a distinct kind of quark with its own mass, electric charge, and role in weak interactions. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. The change from one arrangement to the other is small enough to fit into a single line of notation. It is also enough to change the identity of the particle. The proton carries 1 unit of positive charge. The neutron carries none. The arithmetic is simple. 2 up quarks contribute 4/3 of a positive charge, while 1 down quark contributes 1/3 of a negative charge. The result is positive 1. In the neutron, 1 up quark contributes positive 2/3, and 2 down quarks contribute negative 2/3. The result is 0. Yet the neutron is not electrically blank. Its interior contains moving charged objects, and those charges do not occupy the same places in the same ways. Experiments reveal this indirectly. A beam of electrons can be directed toward neutrons bound inside suitable targets. The electrons carry electric charge, so their paths respond to the distribution of charge within the neutron. By measuring the angles and energies at which they scatter, physicists reconstruct a kind of map. It is not a picture in the ordinary sense. It is a mathematical portrait assembled from many collisions. That portrait shows a neutron with a slight positive tendency near its center and a more negative tendency farther out. The details depend on how the structure is described, because the neutron is a quantum object rather than a tiny solid globe. Still, the central lesson remains. Neutrality is the sum of internal parts. It is not the absence of them. The neutron also has a magnetic moment. A neutral object can respond to magnetic fields when electric charges move inside it. The quarks carry charge and spin, and their motion contributes to a small internal magnetism. The measured magnetic moment became one of the early signs that the particle could not be elementary and featureless. Spin itself requires care. The word suggests a top turning around an axis, but a neutron is not a little sphere rotating through space. Spin is an intrinsic quantum property. It determines how the particle responds to magnetic fields, how it combines with other particles, and which quantum states it may occupy. The neutron has spin 1/2, placing it in the family of particles called fermions. Fermions obey the Pauli exclusion principle. Two identical fermions cannot share the same quantum state. This rule helps organize electrons in atoms, nucleons in nuclei, and matter inside neutron stars. It also shapes the neutron from within, because quarks are fermions too. Their combined state must satisfy strict symmetry rules involving spin, flavor, and color charge. Color charge is the property linked to the strong interaction. The name borrows from red, green, and blue light, but no visible color exists inside the neutron. A quark labeled red is not red in any optical sense. The labels describe three possible forms of strong charge. A neutron as a whole is color neutral because its valence quarks combine into a balanced state. The idea of color solved a problem that appeared when physicists tried to build consistent models of particles made from quarks. Some combinations seem to place identical quarks in states forbidden by the exclusion principle. Adding color supplied another quantum property, allowing the full state to remain valid. It became part of the foundation of quantum chromodynamics. Quantum chromodynamics, often shortened to QCD, is the theory of quarks and gluons. The word chromodynamics refers to color charge, not visible color. In this theory, quarks exchange gluons, and gluons carry the strong interaction. The neutron is not held together by contact or a mechanical shell. It exists as a bound quantum state of quarks and gluon fields. The image of three marbles inside a bag fails almost immediately. The valence quarks do not follow little circular paths. Their positions and momenta are described by probability amplitudes. Gluons are exchanged continuously. Quark and antiquark pairs contribute to the internal state. The boundaries of the neutron are not hard edges but regions where its fields and probability distributions become small. Its size is usually described on the scale of about 1 femtometer, 1/4,000,000th of a meter. At that scale, ordinary intuition weakens. There is no clean surface to touch. There is no empty interior surrounding three separate objects. The neutron is better understood as a concentrated pattern of fields, charges, and motion that behaves as one particle when observed from outside. Even the phrase one-up quark and two-down quarks refers mainly to the net content. Inside the neutron, additional quark and antiquark pairs can appear as part of the quantum field. A temporary up quark may be accompanied by an up antiquark, so their net contribution cancels. The three valence quarks define the neutron, but they do not describe everything present within it. The gluons carry much of the activity. Unlike photons, which do not carry electric charge, gluons themselves carry color charge. That allows gluons to interact with other gluons. The field can branch, combine, and reshape itself. This self-interaction is one reason the strong force behaves so differently from electromagnetism. Two beams of light can cross without sticking together. Gluons do not have that simplicity. Because they carry the charge associated with their own force, they contribute to the structure they are transmitting. The result is a field that is dense, changing, and difficult to separate into independent pieces. At very short distances, quarks can behave almost as though they are loosely connected. This property is called asymptotic freedom. When quarks come very close, the effective strong interaction becomes weaker. As the distance grows, the interaction strengthens. The behavior runs against the familiar pattern of gravity and electromagnetism, both of which weaken with distance. QCD is a quantum theory, so its full behavior is described through fields and probabilities. Still, the broad picture is reliable. Quarks are difficult to separate because the energy stored in the color field rises as the distance between them increases. The field between separating quarks becomes concentrated into a narrow region, often described as a flux tube. Pulling the quarks farther apart adds energy to that tube. Eventually, Enough energy is present to create a new quark and antiquark pair. The attempt to isolate one quark ends with new color-neutral particles instead. Particle accelerators reveal this through jets. When energetic collisions scatter quarks and gluons, the colored particles do not travel freely into detectors. They produce cascades of hadrons, particles made from quarks, antiquarks, and gluons. The detector records narrow sprays extending away from the collision point. A jet is not a photograph of a lone quark. It is the visible trace of confinement. No free quark has been observed. Every known quark appears inside a color-neutral combination. 3 quarks can form a baryon, such as a proton or neutron. A quark and an antiquark can form a meson, such as a pion. Other combinations are possible, including tetraquarks and pentaquarks, but their total color still resolves into neutrality. The neutron belongs to the baryon family. Its 1-up quark and 2 down quarks are joined through the strong interaction into a single state. Nothing in that state is still. Nothing resembles the calm dot once drawn at the center of an atom. Yet the whole particle can remain stable inside many nuclei for times longer than planets have existed. The next layer lies in the force that makes such stability possible. The neutron's quarks cannot be removed one by one. The gluon field does not loosen as they separate. It tightens. To understand the neutron's mass, its endurance, and the energy hidden within ordinary matter, the strong interaction must be followed deeper into the dark space between its quarks. The strong interaction does not resemble any force felt at human scale. Gravity weakens as distance grows. Electric attraction and repulsion weaken in the same way. The field-binding quarks behaves differently. Within the neutron, separation does not bring release. It brings more resistance. At very short distances, quarks can move with a degree of freedom that seems contradictory. When 2 quarks are extremely close, the effective interaction between them becomes weaker. This is asymptotic freedom, a property discovered through quantum chromodynamics and confirmed through high-energy experiments. The closer the quarks are forced together, the less tightly the strong interaction appears to grip them. Inside the narrowest regions of a collision, they behave almost like free particles. The freedom does not last. As the distance between quarks increases, the interaction strengthens. The color field does not spread outward and fade, as an electric field would. It gathers into a narrow tube of energy, joining the colored objects. The tube can be imagined as a line under tension, although no physical cord is present. Pulling the quarks farther apart lengthens this region and raises the energy stored within it. A quark cannot simply drift away from the neutron. The farther it travels, the more energy is required. Soon the field contains enough energy to create matter. A new quark and antiquark pair appears, and the original attempt at separation produces 2 color-neutral particles rather than one isolated quark. The field has not broken the rule of confinement. It has rearranged the available energy into new bound states. This is why detectors never record a single quark arriving alone. High-energy collisions can strike quarks hard enough to redirect them, but the outgoing colored objects immediately begin forming hadrons. Pions, kaons, protons, neutrons, and other particles emerge in narrow streams called jets. The direction of a jet preserves information about the quark or gluon that began it. The quark itself is never seen as a free object. A jet forms through a process called hadronization. Energy in the color field produces repeated quark and antiquark pairs. These combine in many ways as the system expands and cools. By the time the particles reach a detector, the original quark has become part of a whole spray. The neutron is held together by the same principle. Its valence quarks remain confined because any path toward separation raises the energy of the color field. They do not need a rigid container. The field itself defines the bound state. The edge of the neutron is not a wall, but the region beyond which the probability of finding its constituents falls away. Gluons make this behavior possible. They are the carriers of the strong interaction, but unlike photons, they are not neutral under the force they transmit. A photon carries energy and momentum while carrying no electric charge. A gluon carries a combination of color and anticolor. It can therefore interact with other gluons, emit them, and absorb them. This self-interaction changes the structure of the field. Electromagnetic fields can be added together with relative simplicity because photons do not directly respond to other photons under ordinary conditions. The gluon field is nonlinear. One part influences another. The energy stored within it becomes a participant rather than a passive messenger between particles. The neutron's interior is not built from quarks alone. Gluons carry momentum, energy, and part of the particle's spin. They are constantly exchanged within the quantum state. Quarks and antiquarks appear as fluctuations tied to the same field. The neutron's identity remains stable even though its internal pattern changes from moment to moment. The term strong force is sometimes used for two related effects. At the deepest level, quantum chromodynamics binds quarks inside protons and neutrons. At the scale of the nucleus, a residual part of that interaction binds protons and neutrons to one another. The two are connected, but they are not identical descriptions. The first acts directly on color charge. The second appears between particles that are already color neutral. Within the neutron, the direct interaction dominates. Color charge comes in three forms, and the full state combines into neutrality. The labels red, green, and blue are convenient. But the actual quantum state is not a frozen assignment where one quark stays red forever. Gluon exchange changes the color state continuously. A quark can emit a gluon and shift from one color to another, while the total combination remains neutral. Nothing visible changes during this exchange. The neutron still presents the same overall charge, mass, and spin, yet the balance beneath those properties is moving. The apparent simplicity of the particle comes from the stability of the whole pattern, not from stillness among its parts. At the energies of ordinary nuclear physics, QCD becomes difficult to calculate with simple approximations because the coupling is strong. Physicists often use lattice QCD, a method that places the theory on a discrete grid of space and time and evaluates the behavior numerically. These calculations reproduce many known properties of protons, neutrons, and other hadrons. Lattice QCD does not turn the neutron into a familiar mechanical object. It provides a way to follow the underlying fields while preserving the rules of the theory. The results show that the mass and structure of the neutron emerge from a collective quantum state. No single constituent carries the full explanation. Evidence for QCD comes from many directions. Deep inelastic scattering reveals point-like constituents. Jets reveal quarks and gluons, leaving high-energy collisions only through their hadronic descendants. The changing strength of the interaction with energy matches asymptotic freedom. The spectrum of known hadrons fits patterns predicted from quark combinations. Separate experiments converge on the same framework. The force is powerful, but direct comparisons with gravity can mislead. Gravity is weak between elementary particles, yet it reaches across unlimited distance and adds over enormous amounts of matter. The strong interaction is dominant inside hadrons, but confined to a tiny domain. Its reach is short, its effects local, and its influence hidden inside matter. A hand resting on a table does not feel the quark-level strong interaction directly. The sensation of solidity comes mostly from electromagnetic repulsion between atoms and from quantum rules preventing electrons from occupying the same states. The strong interaction works deeper down, maintaining the nucleons that make the atoms possible. Its contribution is still present in every ordinary object. The neutron's quarks have small intrinsic masses, but the bound state weighs far more than their simple total. Energy in the gluon field, motion of the quarks, and the structure of the quantum vacuum all contribute. The strong interaction does not merely hold mass together. Much of the mass appears through the binding itself. The neutron is not heavy because three tiny pieces happen to weigh nearly as much as the whole. The pieces account for only a small fraction. The rest comes from energy contained in motion and fields. The force that prevents the quarks from escaping also gives the neutron most of its weight. Mass and energy are two descriptions of the same physical quantity. Energy confined within a system contributes to the system's mass. A compressed spring weighs slightly more than the same spring after releasing its stored energy. The difference is too small to notice in daily life. Inside the neutron, stored and moving energy is the main contribution. A neutron is smaller than anything that can be resolved through ordinary imaging. Within that space, the color field shifts, gluons exchange momentum, and quarks move in a relativistic quantum state. From outside, the result is a particle that can remain in a nucleus without revealing any of that activity. No part is motionless. The uncertainty principle prevents a quark confined to such a small region from having both a sharply defined position and a sharply defined momentum. Tight confinement requires a broad range of possible momenta. The quarks therefore carry substantial kinetic energy. Their motion is not a hidden orbit but part of a spread-out quantum state. The neutron holds all of this without a shell, surface, or central anchor. It is a stable pattern in the strong field. The pattern can travel through space, scatter from other particles, and join a nucleus. It can also be altered by another interaction entirely. The strong force can confine a down quark, but it cannot guarantee that the quark will always remain down. That change belongs to the weak interaction. Before reaching it, the source of the neutron's mass must be followed more closely, because the same fields that imprison its quarks also account for nearly all the weight of ordinary matter. The neutron carries almost the same mass as the proton, and both are far heavier than the simple sum of the quarks used to classify them. An up quark has only a small intrinsic mass. A down quark is slightly heavier, but still light compared with the neutron as a whole. Adding one up quark and two down quarks accounts for only a small part of what a neutron weighs. The rest does not hide inside another undiscovered solid object. It appears through energy. This is where the familiar equation linking mass and energy becomes more than a symbol. Energy stored in motion, fields, and interactions contributes to the mass of a bound system. The neutron contains quarks moving in a confined quantum state, gluon fields carrying energy between them, and a shifting sea of quark and antiquark contributions. The particle's mass is the total energy of that entire state, measured in its own rest frame. The quarks themselves receive their intrinsic masses through interaction with the Higgs field. That field is present throughout space, and elementary particles couple to it with different strengths. The stronger the coupling, the larger the intrinsic mass. The Higgs boson, observed at CERN in 2012, is an excitation of that field. Its discovery confirms that this mechanism belongs to nature rather than mathematics alone. Yet the Higgs field is not the main source of the neutron's mass. It gives the up and down quarks their small rest masses, but most of the neutron's weight comes from quantum chromodynamics. The strong interaction keeps energy confined inside the particle. The quarks carry kinetic energy. The gluon field carries energy. The quantum state itself contains contributions that do not reduce to three separate masses placed side by side. A useful comparison comes from a box filled with light. Photons have no rest mass, but light trapped inside a perfectly reflecting box adds to the mass of the box because the system contains more energy. The neutron is far more complicated, but the principle is the same. Energy held within a bounded system contributes to inertia and gravity. The system becomes harder to accelerate because more energy is present. The neutron, therefore, owes most of its mass to activity rather than still substance. Its weight is a measure of confined energy. Ordinary matter feels solid and heavy partly because every proton and neutron contains this internal energy. A stone, a drop of water, a bone, and a distant planet all carry mass dominated by the strong interaction inside their nucleons. This does not mean matter is unreal or made from nothing. Fields are physical. Energy is measurable. The neutron scatters, gravitates, and resists acceleration with a definite mass. The point is that mass need not belong only to small, permanent objects. It can emerge from the way a system is organized and from the energy required to maintain that organization. The same idea appears in nuclei, molecules, and larger systems, though the size of the effect changes. Binding energy can lower the mass of a nucleus, compared with the separate masses of its protons and neutrons. Chemical binding also changes mass, but by an amount too small for ordinary scales. Inside a nucleon, the strong interaction works at such high energy that its contribution becomes dominant. Lattice QCD calculations allow physicists to estimate this contribution from first principles. Space and time are represented on a finite grid, and the behavior of quark and gluon fields is evaluated numerically. The calculations are demanding because the fields interact with themselves and with one another. Even so, they reproduce the masses of protons, neutrons, and many other hadrons with increasing precision. The neutron is not a bag containing a fixed amount of gluon energy in one place. Its internal state is spread across possible configurations. In one part of the quantum description, a gluon may carry a certain fraction of momentum. In another, a quark and antiquark pair contributes briefly to the structure. The measured particle is the stable result of all these possibilities combined. Deep inelastic scattering helps reveal how the neutron's momentum is shared. High-energy electrons or other probes strike the nucleon and respond to its internal constituents. The pattern shows that the valence quarks do not carry all the momentum. Gluons and C-quarks account for much of what is missing. The neutron's simple label contains a much larger distribution beneath it. Spin follows a similar story. The neutron has total spin 1/2, but that total cannot be explained by adding the spins of 3 stationary quarks in a simple way. Quark spin contributes. Gluon spin contributes. Orbital motion within the quantum state contributes. The complete accounting remains an active area of study, though the broad structure is known. This became known historically as the nucleon spin problem. Early experiments suggested that quark spins supplied much less of the proton's spin than expected. Later work showed that gluons and orbital angular momentum carry part of the total. The neutron belongs to the same family of questions. Its spin is simple from outside and distributed among several forms of motion inside. Its magnetic moment also reflects this internal arrangement. Because quarks carry electric charge, their spin and motion create magnetic effects. The neutron's total charge is 0, but its magnetic moment is not. A truly point-like neutral particle without charge structure would not behave this way. Measurements of neutron magnetism therefore offer another window into the hidden movement inside. The charge distribution adds more detail. The positive contribution from the up quark and the negative contributions from the down quarks do not cancel at every location. They cancel only in total. Scattering experiments indicate that the neutron has a slight spatial separation between positive and negative tendencies. The exact distribution is described through form factors, quantities that encode how the particle responds to momentum transferred by a probe. Form factors change as the probing energy changes. At low momentum transfer, the neutron appears nearly featureless. At higher momentum transfer, smaller scale structure becomes visible. This is much like viewing a landscape first from far above and then from closer range. The object has not changed. The resolution has. Nothing inside the neutron can be assigned a perfectly sharp position at every instant. Quantum fields do not arrange themselves into a fixed miniature sculpture. The language of probability is not a sign of missing information. It is part of the physical description. What exists is a state with measurable averages, correlations, and response patterns. The neutron's mass, spin, magnetic moment, and charge distribution all arise from the same underlying state. They are not separate decorations added to a basic particle. They are different ways that the internal quark and gluon system appears when tested. A magnetic field reveals one aspect. A scattering experiment reveals another. Gravity and inertia reveal the total energy. From the outside, the neutron remains calm enough to be treated as one particle. It has a stable identity while bound in many nuclei. It can move slowly through a laboratory beam or remain locked inside ancient matter. The fields within it continue their motion without causing the particle to lose coherence. That coherence is not absolute. Another force can alter the balance. The strong interaction preserves quark flavor even while exchanging color and momentum. An up quark remains an up quark under strong interactions. A down quark remains down. The weak interaction follows a different rule. It can change one flavor into another. That ability becomes decisive when the neutron is removed from a stable nucleus. The particle still carries the same mass generated mostly by the strong interaction. Its quarks remain confined. Its magnetic moment and charge distribution remain. Yet the small difference between the masses of the neutron and proton opens a lower energy path. One down quark can become an up quark, and the neutron's identity can change with it. Before that decay is followed in detail, the central point can remain for a moment. Nearly all the mass of ordinary visible matter is not the direct weight of elementary quarks. It is the energy of confinement, motion, and fields inside protons and neutrons. The world feels heavy because the strong interaction never rests. A neutron inside a stable nucleus can remain unchanged for longer than the age of Earth. The same neutron, once removed from that environment, is no longer protected by the surrounding energy structure. Its quarks remain confined. The strong interaction continues to hold them together. Nothing appears to break, yet the particle has become unstable. A free neutron does not decay because the strong force weakens, or because the neutron slowly runs out of energy. Its internal state still exists as a bound system of quarks and gluons. The change comes from another interaction, one that acts far more quietly. The weak interaction can alter quark flavor. A down quark can become an up quark, and that single change is enough to turn a neutron into a proton. The process is called beta-decay. It begins with a neutron containing one up quark and two down quarks. One down quark changes into an up quark. The remaining combination is then two up quarks and one down quark, which is the quark content of a proton. The particle has not merely lost a small piece. Its identity has changed. Electric charge must remain balanced throughout the transition. A down quark carries negative 1/3 of the elementary charge. An up quark carries positive 2/3. The difference is one full unit of positive charge. To preserve the total, the weak interaction produces a negatively charged contribution at the same moment. In the language of the Standard Model, the changing quark couples to a W- boson. The W- is one of the carriers of the weak interaction, together with the W+ and the neutral Z boson. The W- then gives rise to an electron and an electron antineutrino. The final products are a proton, an electron, and an electron antineutrino. The W- boson in this process is not produced as a free particle that could travel into a detector. The neutron does not contain enough available energy to create an on-shell W boson with its full rest mass. Instead, the W appears as an internal part of the quantum interaction, what physicists describe as a virtual exchange. It links the changing quark to the electron and antineutrino, without existing as an independently observable particle. This description avoids the familiar image of energy being borrowed from nothing and repaid before anyone notices. That image can be memorable, but it is not how the theory is actually organized. Quantum field theory calculates the transition as a set of allowed amplitudes. The virtual W is part of that calculation, not a free object with a measurable lifetime inside the neutron. The decay is possible because the neutron is slightly heavier than the combined rest masses of the proton and electron. The neutron has a rest energy of about 939.565 mega-electronvolts. The proton has about 938.272 mega-electronvolts. The electron adds about 0.511 mega-electronvolts. After those masses are accounted for, roughly 0.782 mega-electronvolts remain available. That small amount becomes kinetic energy. The proton recoils gently because it is much heavier than the other products. The electron and antineutrino carry most of the motion away. Energy and momentum are conserved in every decay, though the shares vary from one event to another. The electron does not always emerge with the same energy. Sometimes it carries a large fraction of the available amount. Sometimes the antineutrino carries more. This continuous range once created a serious problem for physics. If beta decay produced only a proton and an electron, the electron should leave with one fixed energy. Experiments showed otherwise. In the early 20th century, the missing energy seemed to threaten one of the most reliable rules in science. Niels Bohr briefly considered whether energy conservation might fail in nuclear events. Wolfgang Pauli proposed another possibility in 1930. A light, neutral particle could be leaving unseen, carrying whatever energy and momentum the electron did not take. Pauli's particle was later named the neutrino by Enrico Fermi. The name means little neutral one. In neutron decay, the emitted particle is the electron antineutrino, the antimatter partner, associated with the electron neutrino. It carries no electric charge and interacts only through the weak interaction and gravity. Its interaction with matter is so rare that an antineutrino born in a decay can cross enormous distances without touching another particle. Billions of neutrinos from the Sun pass through each square centimeter of Earth every second. Nearly all continue through the planet as though rock, metal, water, and living tissue were almost empty. The antineutrino restores the accounting. Energy remains conserved. Momentum remains conserved. Angular momentum remains conserved. The range of electron energies no longer signals a broken law. It reveals that a third particle is sharing the available motion. Fermi developed the first successful theory of beta decay during the 1930s. The modern electroweak theory later placed the process within a larger framework. The W and Z bosons were directly observed at CERN in the early 1980s, confirming a central part of that description. The weakness of the interaction explains the neutron's relatively long life. Strong interaction processes often occur on timescales near a tiny fraction of a trillionth of a second. A free neutron survives for hundreds of seconds. In particle physics, that is a long pause. An individual neutron does not carry a visible countdown. Quantum decay does not assign a known moment in advance. One neutron may decay soon after becoming free. Another may remain for much longer. Only a large collection reveals the statistical pattern. The mean lifetime is close to 880 seconds, a little under 15 minutes. The half-life is somewhat above 10 minutes, meaning that half of a large initial population will have decayed by then. Mean lifetime describes the average scale of an exponential decay law. Half-life marks the time required for a population to fall by half. The exact value has become its own puzzle because different experimental methods do not agree perfectly. That disagreement belongs to the next part of the story. For now, the broad fact is secure. A free neutron lasts minutes, not geological ages. The source of the instability lies in a delicate mass difference. The down quark is intrinsically heavier than the up quark. Since the neutron contains two down quarks, while the proton contains one, this tends to make the neutron heavier. Electromagnetic effects push in the opposite direction because the proton's positive charge adds field energy. The final balance leaves the neutron heavier by a little more than 1 mega-electron-volt. The margin is small compared with the total mass of either particle. Still, it decides which one can decay in empty space. The neutron can move toward the lighter proton state while releasing energy. A free proton cannot spontaneously become a neutron because the final state would be heavier and would require additional energy. This tiny ordering supports the structure of ordinary matter. Stable hydrogen contains a single proton. If the proton were the heavier and unstable particle under ordinary conditions, hydrogen would not persist in the same form. Stellar burning, chemistry, and the long history of matter would follow another path. Free neutrons appear in cosmic ray interactions, nuclear reactions, and particle collisions. If they do not enter a nucleus, each carries a growing probability of becoming a proton, an electron, and an antineutrino. Nothing inside the neutron explodes. The quarks do not escape confinement. The strong field remains present before and after the transition. One quark changes flavor through the weak interaction, and the entire bound state reorganizes around the new combination. A neutron becomes a proton, while two light particles carry away charge, energy, momentum, and angular momentum. The change leaves no flash visible to the eye. Yet it is one of the basic transformations shaping nuclei, stars, and the early universe. The weak interaction acts slowly, but given enough time it changes what matter is allowed to become. A free neutron, therefore, lives between two kinds of order. The strong interaction keeps its quarks confined. The weak interaction allows one of those quarks to change. Confinement preserves the particle long enough for decay to have meaning, while the small mass difference opens a path toward a lower energy state. The mechanism is understood in great detail. The exact lifetime is less settled. Two families of experiments watch free neutrons in different ways, and their clocks do not quite agree. That quiet mismatch has lasted for years, waiting inside measurements separated by only a few seconds. Measuring the lifetime of a neutron sounds, at first, like a simple exercise. Place a group of free neutrons somewhere quiet, wait, and count how many remain. The decay law is known. The mathematics is familiar. Yet the particle itself makes the experiment difficult from the first moment. A neutron carries no electric charge, so an electric field cannot hold it in place. It passes through many materials without leaving a clear signal. Even when it disappears, the experiment must separate true beta decay from every other way a neutron might be lost. Two main methods have grown from that difficulty. One stores very slow neutrons and counts the survivors. The other sends neutrons through a beam and counts the protons created when some of them decay. Both are intended to measure the same mean lifetime. For years, they have returned values separated by roughly 9 or 10 seconds. The stored neutron method begins by slowing neutrons until they move at only a few meters per second. These are ultra-cold neutrons. Their motion is gentle enough for gravity, magnetic fields, or carefully chosen material surfaces to confine them. A trap is filled, held closed for a measured interval, and emptied into a detector. The number recovered after a short wait is compared with the number recovered after a longer one. The rate at which the population falls gives the lifetime. Older bottle experiments often used material walls. That choice created a quiet complication. A neutron missing from the final count might have undergone beta decay, but it might also have been absorbed by the wall, scattered into an undetectable path, or gained enough energy to escape. Each non-decay loss had to be measured and corrected. A small mistake in that correction could shift the final lifetime. Magnetogravitational traps reduce this problem by keeping ultra-cold neutrons away from ordinary walls. Their magnetic moments respond to a shaped magnetic field, while gravity prevents them from rising out of the open top. The apparatus developed by the UC&Tau collaboration resembles a broad bathtub lined with magnets. Neutrons are loaded into the trap, allowed to remain for different intervals, and then counted by lowering a detector into the stored population. The neutrons move so slowly that the description, walking speed, is almost literal. They drift, rise, fall, and turn within the magnetic bowl. Some remain for only a short storage period. Others are held much longer. The difference between the surviving populations reveals how quickly decay has emptied the trap. In 2025, an updated UC&Tau analysis reported a mean lifetime of 877.83 seconds, with an uncertainty below 0.3 of a second. It is the most precise single measurement reported so far. The result agrees with earlier high-precision bottle measurements. The clock made from trapped survivors appears steady. The beam method watches the same decay from another direction. A stream of cold neutrons passes through a carefully defined region. Most continue onward unchanged. A small fraction decay while crossing the apparatus. Each decay creates a proton, an electron, and an antineutrino. The proton carries positive charge, so magnetic and electric fields can collect it, even though the original neutron could not be held that way. At NIST, a proton trap surrounds part of the neutron beam. Protons born inside that region are confined, stored briefly, and then directed toward a detector. At the same time, the experiment measures how many neutrons pass through. The lifetime is inferred from the number of decay protons compared with the neutron flux and the time each neutron spends inside the measured volume. This method does not ask how many neutrons vanish. It asks how many expected decay products appear. That distinction matters. A bottle experiment is inclusive. Anything that removes a neutron from the stored population can imitate decay unless it is controlled. A beam experiment is selective. It counts a particular product of the ordinary beta, decay channel, while relying on an exact measurement of the number of neutrons passing through. The best established NIST beam result gives a lifetime near 887.7 seconds, with an uncertainty of a little more than 2 seconds. The central value is close to 10 seconds longer than the UCN tau result. Each method has undergone years of calibration and repeated checks. Each family of experiments is internally consistent enough that the gap cannot be dismissed as ordinary statistical wandering. 10 seconds is small beside the age of a person or the life of a star. It is not small beside an experimental uncertainty below 1 second. The disagreement is therefore called the neutron lifetime puzzle. The first explanation considered is usually the least exotic one. Experiments are not abstract equations. They contain detectors, magnetic fields, surfaces, apertures, backgrounds, calibrations, and particles that do not always move as simply as expected. Bottle experiments must understand marginally trapped neutrons, detector efficiencies, changes in the stored energy distribution, and any path by which neutrons escape without decaying. Beam experiments must know the neutron flux, the effective trapping volume, the proton detection efficiency, and the behavior of charged particles near the ends of the trap. A hidden, systematic effect in either method could move one value toward the other. This remains the leading practical concern. New experiments are being designed with different geometries and different ways of counting, because a changed method brings a changed set of possible errors. The disagreement has also encouraged proposals beyond the standard model. Some models suggest that a small fraction of neutrons might transform into particles that ordinary proton counting experiments would not see. Other proposals involve mirror neutrons, or weakly interacting dark sector states. If such a channel existed, a bottle would register the neutron as gone, while a beam experiment counting ordinary decay protons might miss the event. The two clocks would then be measuring slightly different things. No such explanation has been confirmed. Dedicated searches have placed strong limits on many versions of these ideas. The gap is therefore not evidence that a hidden decay has been found. It is an open measurement problem with several possible sources, most of them still tied to experimental systematics. The lifetime matters beyond the laboratory. In the first minutes after the Big Bang, free neutrons were disappearing through beta decay while nuclear reactions began locking some of them into helium. A difference of several seconds changes the predicted amount of primordial helium by a small but measurable amount. The lifetime also enters precision tests of the weak interaction and the consistency of quark mixing in the standard model. This gives the disagreement an unusual reach. One clock is built from neutrons moving slowly inside a magnetic bowl. Another is built from protons collected beside a cold beam. Their separation affects calculations that extend back to the early universe. The next generation of experiments is intended to narrow the space between them. Larger beam apparatus can collect many more decay protons and test systematic effects over a wider range. Improved ultra-cold neutron traps can increase the stored population, reduce detector uncertainty, and examine whether particular trajectories survive differently from others. Some experiments aim to detect decay electrons rather than protons, creating a third path between the two established methods. The answer may eventually be ordinary. A calibration may shift. A loss mechanism may become visible. Two numbers may settle into one. It is also possible that the mismatch points toward a process not yet included in the usual description. The honest position remains between those possibilities. The neutron has already shown that apparent simplicity can hide a moving interior. Its lifetime now carries a similar lesson. The decay mechanism is understood. The final particles are known. The weak interaction has been tested across many settings. Still, when two careful clocks are asked how long a free neutron lives, they do not yet give exactly the same answer. For the moment, the neutron's time is written in two nearby numbers. One comes from counting those that remain, the other comes from counting what their deaths leave behind. Between them lies a gap of only a few heartbeats, small enough to overlook in daily life and large enough to keep an entire field measuring the silence. A neutron does not become a different particle when it enters a stable nucleus. Its quark content remains one up quark and two down quarks. The strong interaction still confines those quarks, and the weak interaction still allows one of the down quarks to change flavor. Nothing inside the neutron has switched off. What changes is the energy of the larger system surrounding it. A free neutron exists on its own. Its mass is greater than the combined rest masses of a proton and an electron, with enough energy left for the electron, antineutrino, and recoiling proton to move away. The decay is permitted because the final state lies lower in energy. Inside a nucleus, the neutron belongs to a bound structure. The energy of the whole structure must be counted. Binding lowers the total energy. When protons and neutrons join to form a nucleus, energy is released. The resulting nucleus has less mass than the same nucleons would have if separated and weighed individually. The missing mass has left as radiation or motion. The amount required to separate the nucleus again is called the binding energy. This can be imagined as a landscape. A free particle rests on open ground. A bound particle lies in a depression. To remove it, energy must be supplied so that it can climb out. The depression is not a physical hole in space. It represents the energy of the system. Lower states are more stable because there is nowhere lower for them to go without. The same picture explains why beta decay may be allowed in one nucleus and forbidden in another. If a neutron inside a nucleus changes into a proton, the nucleus gains one proton and loses one neutron. That produces a different element. The energy of the daughter nucleus may be lower or higher than the original. Only a lower final state allows spontaneous decay. A stable nucleus is arranged so that the proposed final state costs too much. The new proton would enter an existing nuclear environment. It would feel strong nuclear attraction from nearby nucleons, but it would also add electric repulsion because every proton carries positive charge. The daughter nucleus may therefore sit higher in energy than the parent nucleus. Quantum structure adds another limit. Protons and neutrons are fermions, and fermions obey the Pauli exclusion principle. They occupy available quantum states in a layered pattern. A newly created proton cannot take any position it wants. If the lower proton states are filled, it must enter a higher one. That raises the energy required for the transition. The weak interaction still permits a down quark to become an up quark. The pathway remains. But a pathway is not enough. Energy, momentum, electric charge, and angular momentum must all balance. If no final arrangement satisfies those conditions at a lower total energy, the decay does not proceed. This is not a battle in which the strong force blocks the weak force. The strong interaction creates the bound nuclear structure. The weak interaction allows flavor change. The strong interaction protects the neutron indirectly by shaping a system in which the allowed weak transition would lead uphill. Helium-4 provides a clear example. Its nucleus contains two protons and two neutrons. It is tightly bound. If one neutron changed into a proton, the result would contain three protons and one neutron. The added electric repulsion and altered nuclear structure place the possible final state above the original one. The decay would require energy rather than release it. The neutron, therefore, remains. Nothing restrains it moment by moment like a mechanical lock. The entire nuclear state simply has no lower energy destination available through that decay channel. Carbon-12 follows the same broad rule. Its 6 protons and 6 neutrons form a stable arrangement. Turning one neutron into a proton would create a nitrogen nucleus with 7 protons and 5 neutrons. The relevant final state would not lie below the original carbon nucleus. The decay is closed. Carbon-14 is different. It contains 6 protons and 8 neutrons. That excess shifts the energy balance. One neutron can change into a proton, producing nitrogen-14 with 7 protons and 7 neutrons. The daughter nucleus lies lower in energy, so beta decay becomes possible. The process is slow, with a half-life of thousands of years, but it is allowed. The contrast lies between two complete nuclear systems. Carbon-12 offers no downhill path. Carbon-14 does. This is why the phrase stable neutron can be misleading. Stability does not belong only to the particle, it belongs to the state. A neutron may be unstable when free, stable in one nucleus, and unstable again in another. The surrounding nucleons change the available energies without changing the neutron's identity before the decay. The binding energy comes from the residual strong interaction between nucleons. Protons and neutrons are color neutral, yet the strong interaction within them leaves a short-range effect between neighboring nucleons. This nuclear force is attractive over distances comparable to the size of a proton and neutron. At shorter distances, it becomes repulsive, preventing nuclei from collapsing into a single point. The range is brief. A nucleon mainly feels the attractive nuclear force of its nearest neighbors. Electric repulsion behaves differently. Every proton repels every other proton across the nucleus. In small nuclei, the short-range attraction dominates easily. In larger nuclei, the long-range electric repulsion accumulates. Neutrons help without adding electric charge. They contribute to nuclear attraction while avoiding proton-proton repulsion. Heavy stable nuclei therefore contain more neutrons than protons. The extra neutrons become part of the structure that keeps the nucleus bound. Still, too many neutrons raise the energy again. Additional neutrons must occupy higher quantum states. At some point, converting one of them into a proton lowers the total energy. Beta minus decay then moves the nucleus toward a more balanced arrangement. Too many protons create the opposite problem. A proton may become a neutron through beta plus decay or electron capture if the daughter nucleus lies lower in energy. The direction changes, but the principle remains the same. Nuclear transformations follow the available energy landscape. That landscape is not smooth. Nuclei contain shells and preferred configurations. Certain numbers of protons or neutrons produce unusually stable structures, much as filled electron shells stabilize atoms. These shell effects can change which decays are allowed and how quickly they occur. Even nuclei with similar numbers of particles may have very different lifetimes. The lifetime also depends on how much energy is released and on the quantum details of the transition. A decay with little available energy may proceed slowly. Another with more energy and favorable quantum conditions may occur much faster. The surrounding state determines how easily it can act. This makes nuclear stability a property of context in a precise physical sense. The neutron carries its mass, spin, magnetic moment, and quark structure wherever it goes. Yet those properties alone do not decide its fate. The total state includes nearby nucleons, their arrangement, their energy levels, and the forces between them. The difference between minutes and billions of years can therefore arise without altering the particle itself. A free neutron sits above an available lower state and decays. A neutron in a stable nucleus sits within a configuration from which that same change would raise the energy. One rolls downhill, the other has no downhill direction. The picture of shelter is useful if kept gentle. The nucleus does not hide the neutron from the weak interaction. It gives the neutron a place in a lower energy hole. The protection comes from belonging to a structure whose balance would be disturbed, not improved, by decay. Beyond individual examples, stable nuclei gather along a narrow path defined by the number of protons and neutrons they contain. On either side lie radioactive nuclei that move toward lower energy through beta decay, positron emission, electron capture, or other transformations. That path is known as the Valley of Stability. The valley is the larger map of the same principle. Every nucleus occupies a point in an energy landscape shaped by binding, electric repulsion, quantum states, and particle masses. Some points lie deep, others sit on slopes. The weak interaction provides one of the ways a nucleus can move. The next part follows that valley across the elements, from light nuclei with nearly equal numbers of protons and neutrons to heavy nuclei that require a growing excess of neutrons. Along the way, stability becomes less a fixed label than a position in a landscape that matter is always trying to descend. The Valley of Stability is not a place in space. It is a way of arranging nuclei on a chart, with the number of protons along one direction and the number of neutrons along the other. Stable nuclei gather along a narrow path. Radioactive nuclei lie to either side, and their decays tend to move them back toward lower energy. Among the lightest nuclei, stability often appears near equal numbers of protons and neutrons. Helium-4 has 2 of each. Carbon-12 has 6 of each. Oxygen-16 has 8 of each. The nuclear attraction between neighboring nucleons is strong enough to hold these small systems together, while the electric repulsion among protons remains modest. As nuclei grow, the balance shifts. The nuclear force acts only across short distances, so each nucleon mainly feels its nearest neighbors. Electric repulsion has no such short limit inside the nucleus. Every proton pushes against every other proton. The larger the proton number becomes, the more that repulsion accumulates. Iron-56 has 26 protons and 30 neutrons. Tin-120 has 50 protons and 70 neutrons. Lead-208 has 82 protons and 126 neutrons. The excess grows gradually as the nucleus becomes heavier. The pattern is not arbitrary. It reflects a compromise among several effects. The strong nuclear interaction favors close packing. Electric repulsion pushes protons apart. The Pauli exclusion principle forces identical nucleons into progressively higher quantum states as more are added. Shell structure makes some proton and neutron numbers more stable than nearby values. These influences combine into an energy surface rather than a simple line. A nucleus may sit in a deep basin, on a shallow slope, or near a ridge from which several decay paths are possible. The Valley of Stability traces the lowest region through that surface. A neutron-rich nucleus lies on one side of the valley. It contains more neutrons than the lowest energy arrangement for that proton number. One of those neutrons may undergo beta-minus decay. A down quark changes into an up quark. The neutron becomes a proton, and an electron and electron antineutrino leave the nucleus. The proton number rises by 1 while the total number of nucleons remains the same. Carbon has 6 protons. If one neutron inside a carbon nucleus becomes a proton, the nucleus no longer belongs to carbon. It belongs to nitrogen. Carbon-14 offers a familiar example. Its nucleus contains 6 protons and 8 neutrons. The isotope is created in the atmosphere when cosmic ray processes produce neutrons that participate in nuclear reactions with nitrogen. Carbon-14 then enters carbon dioxide, plants, animals, and the broader exchange of matter in the living world. After an organism dies, that exchange stops. The carbon-14 already present continues to decay with a half-life of about 5,730 years. One neutron becomes a proton, and carbon-14 becomes nitrogen-14. Measuring how much carbon-14 remains allows the age of once-living material to be estimated over many thousands of years. The decay probability remains steady. Ordinary environmental changes do not significantly alter the nuclear transition, though the exact moment for any one atom remains unpredictable. Carbon-14 decays slowly because the available energy is small and the quantum transition is not especially rapid. Other neutron-rich nuclei release more energy or have more favorable transitions, and decay much faster. Some last seconds, some last days. Others persist for millions or billions of years. Potassium-40 survives with a half-life of roughly 1.25 billion years. It decays through more than one pathway, including beta-decay and electron capture. Its long presence inside rocks allows geologists to measure events deep in Earth's history. The same weak interaction that changes a free neutron in minutes can operate inside a nucleus over timescales comparable to the age of a planet. On the opposite side of the valley lie proton-rich nuclei. Here, converting a proton into a neutron may lower the total energy. The change can occur through beta plus decay, in which a proton becomes a neutron while emitting a positron and an electron neutrino. A positron is the antimatter partner of the electron, carrying the same mass and opposite charge. The other route is electron capture. An inner atomic electron is absorbed by the nucleus, where it combines with a proton to form a neutron and an electron neutrino. The vacancy left in the electron shell is then filled by another electron, often releasing X-rays or other radiation. The nuclear change and the atomic rearrangement happen at different scales, but both follow from the same event. Whether beta plus decay or electron capture occurs depends on the energy available. Creating a positron requires enough energy to provide its rest mass and account for the atomic bookkeeping. If that amount is not available, electron capture may still be allowed. Nuclei can also change through alpha decay, spontaneous fission, proton emission, neutron emission, and other processes. These become important especially among very heavy or highly excited systems, yet beta decay has a distinct role. It changes the balance between neutrons and protons without changing the total number of nucleons. That movement is what guides nuclei toward the valley. A neutron-rich isotope steps toward higher proton number through beta minus decay. A proton-rich isotope steps toward higher neutron number through beta plus decay or electron capture. The nucleus changes identity while keeping roughly the same mass number. The binding energy curve reveals another part of the landscape. If binding energy per nucleon is plotted across the elements, the curve rises quickly among light nuclei, reaches a broad maximum near iron and nickel, and then declines slowly among heavier nuclei. This shape explains why both fusion and fission can release energy. Light nuclei can combine into more tightly bound systems, moving upward toward the peak. Very heavy nuclei can split into medium mass fragments that are also more tightly bound. In both cases, the final products have slightly less mass than the starting material, and the difference appears as released energy. Iron-56 is often described as the most tightly bound nucleus, though nickel-62 has a slightly higher binding energy per nucleon. The difference is small, and iron remains central in stellar evolution because of the particular pathways by which stars build nuclei. Once fusion in a massive star reaches the iron region, further fusion no longer provides the same steady release of energy. The valley is therefore linked to the life of stars as well as to laboratory radioactivity. Nuclear reactions build isotopes away from stability. Weak decays then change their neutron-to-proton ratios. Some nuclei settle quickly. Others remain suspended on shallow slopes for immense periods. There are also nuclei once thought stable that may decay on timescales far beyond present measurement. Bismuth-209 was long treated as stable before its alpha decay was observed, with a half-life vastly longer than the current age of the universe. The word stable often means that no decay has yet been detected, not that every possible transition has been proved impossible forever. Some isotopes may undergo double beta decay, a rare process in which two neutrons change into two protons. In the observed form, two electrons and two antineutrinos are emitted. Experiments also search for neutrinoless double beta decay, in which no antineutrinos would appear. Such a discovery would suggest that the neutrino is its own antiparticle and would reveal physics beyond the current standard model. No confirmed observation has yet been made. The valley records the nuclei that last, the ones that move, and the directions their transformations take. Beneath every point lies the same accounting of mass, charge, spin, binding, and allowed quantum states. A nucleus does not seek stability with intention. It occupies a state, and if a lower permitted state exists, there is some probability that a transition will occur. The time may be shorter than a blink or longer than cosmic history. The rule remains unchanged. Following the valley outward eventually reaches nuclei too large and too neutron-rich to be common on Earth. Many appear only in stellar explosions, collisions, or laboratories. Their brief existence becomes a pathway through which the universe builds elements heavier than iron. Before reaching those distant events, the story turns farther back. The first broad distribution of protons and neutrons was set when the universe was only minutes old. The valley had not yet filled with elements. There were only the first light nuclei, forming while free neutrons disappeared one by one. The first stable nuclei formed before there were stars, planets, or atoms. The universe was only minutes old, filled with radiation and particles moving through a heat so intense that no ordinary nucleus could remain intact. Protons and neutrons existed, but they were not yet safely enclosed inside helium or any other lasting structure. They were part of a rapidly changing mixture, and the balance between them was still being decided. In the earliest fraction of a second, matter existed in forms too energetic for isolated protons and neutrons to hold together. Quarks and gluons moved through a hot plasma. As the universe expanded, the temperature fell. Quarks became confined into hadrons, including protons and neutrons. From that point onward, the small difference between their masses began to matter. Weak interactions continually changed one into the other. A neutron could become a proton, while related reactions could turn a proton into a neutron when enough energy was available. Electrons, positrons, neutrinos, and antineutrinos took part in these exchanges. At first, the reactions were fast compared with the expansion of the universe, so the neutron-to-proton ratio stayed close to thermal equilibrium. The ratio was not equal. Neutrons are slightly heavier than protons, and higher energy states are less common in a cooling thermal population. As the temperature dropped, protons became more numerous. The weak interactions still moved particles in both directions, but the balance gradually favored the lighter state. Neutrinos were becoming part of this changing background as well. Earlier, they scattered often enough to share energy with electrons, positrons, and other particles. As expansion lowered the density, those collisions became rare, and neutrinos began traveling almost freely. Their departure did not switch off the weak interaction at a single instant, but it marked the gradual separation of the particle populations that had once remained in close thermal contact. The cooling history of those populations helped determine when neutron-proton conversion could no longer keep pace. Expansion continued. The average distance between particles increased, and the rate of weak reactions fell. Eventually, the universe cooled and thinned faster than those reactions could maintain equilibrium. The neutron-to-proton ratio froze out. This did not mean every weak reaction stopped. It meant the overall balance could no longer adjust quickly enough to follow the changing temperature. At freeze-out, there were roughly several protons for every neutron. The exact ratio depends on the details of the calculation, including the expansion rate and the neutron lifetime. Free neutrons then began to disappear through beta decay, while the universe continued cooling toward the moment when nuclei could survive. A neutron left outside a nucleus does not wait for cosmic conditions to become convenient. Its decay probability remains. During the interval between weak, freeze-out, and nuclear assembly, some neutrons became protons. The surviving fraction would determine how much helium the young universe could make. The first possible nuclear step was the formation of deuterium, a nucleus containing one proton and one neutron. Deuterium is lightly bound. At very high temperatures, energetic photons destroyed it almost as soon as it formed. A proton and neutron could join. But the next collision with radiation could pull them apart again. This delay is called the deuterium bottleneck. The universe contained enough particles to begin nuclear reactions, but the background radiation remained too energetic for deuterium to last. Until that fragile nucleus survived, larger nuclei had no stable path forward. The temperature kept falling. After a few minutes, the high-energy tail of the photon distribution weakened enough for deuterium to remain intact. Nuclear reactions then moved quickly. Deuterium captured protons and neutrons. Helium-3, tritium, and other light intermediates appeared. Most available neutrons eventually entered helium-4, a tightly bound nucleus containing 2 protons and 2 neutrons. Helium-4 became the main refuge for primordial neutrons. Once locked inside that nucleus, the neutron was no longer free to decay in the ordinary way. The energy structure of helium made the beta transition unfavorable. Neutrons that had survived only minutes in open space could now remain bound across the age of the universe. The resulting composition was simple. By mass, ordinary matter emerged as roughly 3/4 hydrogen and 1/4 helium, with small traces of deuterium, helium-3, and lithium. The exact values depend on the baryon density, the number of light particle species, nuclear reaction rates, and the neutron lifetime. Still, the broad pattern is one of the strongest successes of early universe physics. The prediction can be tested against ancient gas. Astronomers study regions with very low concentrations of heavy elements, looking for material that has undergone little processing inside stars. The observed abundance of helium and deuterium agrees closely with the calculations of Big Bang nucleosynthesis. The agreement links nuclear reactions in the first minutes to measurements made billions of years later. The neutron lifetime enters quietly but directly. A shorter lifetime allows more free neutrons to decay before deuterium becomes stable. Fewer neutrons remain for helium, so the predicted helium abundance falls. A longer lifetime preserves more neutrons, raising the helium yield. This is one reason a difference of several seconds between laboratory measurements matters. The effect on primordial helium is small, but modern cosmology works at a precision where small shifts carry meaning. A neutron stored in a magnetic trap and a neutron moving through a beam both contribute to a question that reaches back to the first few minutes after expansion began. The early universe also offers a counterpoint to the idea that helium forms mainly in stars. Stars produce enormous amounts of helium, but much of the helium present before the first stars ignited was already there. It formed in the first nuclear episode, long before gravity gathered gas into galaxies. Hydrogen remained dominant because the nuclear path beyond helium was difficult. Stable nuclei with mass numbers 5 and 8 do not exist. That gap blocked the smooth construction of heavier elements. The universe expanded and cooled too quickly for rare pathways to overcome the barrier in large amounts. Nearly all carbon, oxygen, silicon, iron, and heavier elements therefore had to wait for stars. Primordial nucleosynthesis built the first simple inventory. Stellar interiors later added complexity. The neutron stood at the center of the first inventory. Without enough surviving neutrons, helium could not form in the observed amount. With too many, the early composition would shift. The balance depended on the neutron-proton mass difference, the speed of weak interactions, the expansion rate, and the time available before nuclear reactions began. None of these processes acted with intention. The universe did not preserve a chosen amount of helium. Particles followed the allowed reactions, while temperature and density changed. The final abundance emerged from timing. That timing had several clocks. The expansion of space cooled the plasma. Weak reactions tried to maintain the neutron-proton balance. Free neutrons decayed. Nuclear reactions waited for deuterium to survive. When those clocks crossed, the composition of ordinary matter was set. The sequence lasted only minutes, yet its result remains visible in stars and interstellar gas. Every region of the universe inherited the same broad primordial mixture. Later generations altered it, but they began from that common foundation. Inside modern helium atoms, some neutrons may trace their nuclear history through ancient stars rather than directly to the Big Bang. Individual particles exchange, react, and become part of new nuclei over time. What survives is not a simple identity record for each neutron, but the physical pattern established in the first minutes, the abundance of light nuclei, and the ratio of hydrogen to helium. The early neutron population also helped shape the later pace of stellar evolution. More helium at the beginning changes how gas cools, how stars form, and how long different phases of burning last. The effect is subtle, spread across vast timescales, but the first nuclear balance remains part of every later structure. When the first stars finally formed, they inherited hydrogen, helium, and only tiny amounts of anything heavier. Gravity compressed that material until fusion began. At the center of those stars, protons would once again need the weak interaction to create neutrons. The neutron's role, therefore, did not end when Big Bang nucleosynthesis closed. The first minutes placed neutrons inside helium. The first stars would later create new ones inside their cores, slowly and with great difficulty. That slowness would allow starlight to continue for billions of years. The sun shines because gravity presses its core into a state where nuclear reactions can occur. The temperature there reaches millions of degrees, and the pressure is immense. Yet even under those conditions, fusion does not begin easily. Protons repel one another because they carry the same positive charge. Most collisions end with the particles turning away before the strong nuclear force can bind them. A small fraction approach closely enough for quantum tunneling to matter. Tunneling does not mean the proton breaks through a physical wall. It means the quantum state allows a tiny probability of appearing on the other side of an energy barrier that classical motion could not cross. Even then, reaching close range is only the beginning. The first step of the proton-proton chain requires two protons to form deuterium. A deuterium nucleus contains one proton and one neutron. The collision begins with two protons, so one of them must change identity. An up quark inside one proton becomes a down quark. The proton becomes a neutron, and the weak interaction releases a positron and an electron neutrino. This conversion is rare. The strong interaction can bind nucleons quickly once the right combination exists, but it cannot turn a proton into a neutron. Only the weak interaction can make that change, and the weak interaction acts slowly at the energies found in the solar core. Two protons may meet countless times without completing this first step. That slowness is the reason the sun does not consume its fuel in a brief flash. The core is hot enough for protons to collide continuously, but the weak conversion happens only for a very small fraction of those encounters. Fusion is therefore regulated by the least likely step. Once deuterium forms, later reactions proceed much more readily. The deuterium nucleus captures another proton and becomes helium-3, releasing a gamma-ray photon. Two helium-3 nuclei can later combine to form helium-4, while returning two protons to the surrounding plasma. The net result is that four protons become one helium-4 nucleus, along with positrons, neutrinos, photons, and kinetic energy. The mass of the final helium nucleus is lower than the mass of the four original protons. The difference appears as energy. Some leaves immediately in neutrinos. The rest is shared among particles in the core, heating the surrounding plasma. The energy does not move straight to the surface. Photons are absorbed and re-emitted repeatedly inside the dense solar interior. Their path becomes a long, random walk. Energy gradually passes outward through the radiative zone, and then through moving currents in the convective zone. Only near the surface does it escape into space as sunlight. The neutrinos take another path. They interact so weakly that most leave the sun almost as soon as they are created. Minutes later, they cross Earth. Their arrival provides direct evidence that proton-to-neutron conversion is occurring inside the solar core now, not merely as part of a theoretical model. For many years, detectors observed fewer solar neutrinos than calculations predicted. The solution did not lie in a failing sunday. Neutrinos change flavor as they travel, moving among electron, muon, and tau types. Early detectors were sensitive mainly to electron neutrinos and therefore missed much of the flux. This discovery showed that neutrinos have mass. however small. It also connected the weak interaction inside the Sun with physics beyond the earliest form of the Standard Model. The first step of stellar fusion became a laboratory extending across the distance between the solar core and Earth. The pace of that first step sets the lifetime of a main sequence star. The Sun has been shining for about 4.5 billion years and still contains enough hydrogen in its core to continue for roughly several billion more. Its longevity does not come from an unlimited fuel supply. It comes from the difficulty of using that fuel. A fire on Earth burns quickly when chemical reactions find easy paths. The solar core behaves differently. Its fuel is abundant, but the gateway reaction is restricted. The weak interaction acts like a narrow valve, allowing energy to emerge gradually. A universe with a much faster proton-to-neutron conversion would contain stars with very different lives. Hydrogen could be consumed more rapidly. Stable periods would shorten. The long intervals available for planets to cool, atmospheres to change, and biology to develop could be reduced. Stellar history follows from the measured properties of particles. Small stars press their cores less strongly and burn fuel slowly. They can remain luminous for far longer than the sunday. Massive stars compress their cores more deeply, reach higher temperatures, and drive reactions at much faster rates. They possess more fuel, but they spend it so quickly that their lives may last only millions of years. The neutron enters both ends of that range. In low-mass stars, it appears during the first weak step of hydrogen fusion. In massive stars, later stages build nuclei, containing growing numbers of neutrons and protons. After hydrogen in a stellar core becomes scarce, the structure changes. Gravity compresses the center, while fusion shifts into surrounding layers or begins using heavier fuel. Helium nuclei can combine through the triple alpha process to form carbon. Additional captures produce oxygen. In sufficiently massive stars, further stages build neon, magnesium, silicon, sulfur, and nuclei near the iron region. Each stage operates at a higher temperature and over a shorter interval than the one before. Hydrogen burning may last millions or billions of years. Helium burning is shorter. The final silicon burning stage in a massive star can be completed in days. The sequence ends near iron and nickel because fusion beyond that region no longer releases energy in the same way. Nuclei there are among the most tightly bound. Combining them into heavier nuclei requires an input rather than providing a steady source of heat. The core then loses the support that fusion once supplied. What happens next depends on the star's mass, but in the heaviest cases, the center collapses. Electrons and protons are driven together, producing neutrons and neutrinos through the weak interaction. Matter becomes extraordinarily dense. The neutron returns, now not as a rare product in a slow solar reaction, but as a major component of a collapsing stellar core. Before collapse, stars also create neutrons through nuclear reactions in their interiors. Some of these free neutrons are captured by atomic nuclei. Because neutrons carry no electric charge, they are not repelled by the positive nucleus. They can approach and be absorbed more easily than protons. Slow neutron capture, known as the S process, occurs where neutron production is modest enough that unstable nuclei often have time to beta decay before capturing another neutron. The path moves gradually across the chart of nuclides, building many elements heavier than iron. The neutron capture adds mass without changing the element immediately. Beta decay later changes a neutron into a proton, moving the nucleus to the next element. The sequence repeats: capture, wait, decay, and capture again. In old giant stars, this process can continue over thousands of years. Material enriched with heavy elements is later released through stellar winds. Those atoms enter interstellar clouds and may become part of future stars and planets. Rapid neutron capture follows a different rhythm. In environments with an overwhelming density of free neutrons, nuclei absorb several before beta decay can occur. They are pushed far from the valley of stability. When the neutron flood ends, they decay back toward stable forms, producing many of the heaviest elements. The detailed sites of this R process remained uncertain for decades. Neutron star mergers are now known to provide at least one major environment. Other rare stellar explosions may also contribute. The final answer may involve more than one kind of event: the slow fire of ordinary stars and the sudden neutron-rich events at the end of stellar lives belong to the same larger story. A weak proton-to-neutron conversion begins the chain that allows stars like the Sun to shine. Later, neutron captures help build the heavy nuclei that those stars alone cannot make through fusion. The neutron is therefore present at both the calm beginning and the violent end of stellar evolution. In one setting, its creation is so rare that it keeps a star stable for billions of years. In another, neutrons appear in numbers large enough to reshape entire nuclei within moments. The next part follows matter into the densest remnant left, after a massive star collapses. There, the familiar distinction between separate nuclei begins to fade, and neutrons become part of a state that cannot be reproduced anywhere on Earth. A neutron star begins where an ordinary atomic nucleus ends. In the core of a massive star, gravity drives matter inward until atoms can no longer keep their familiar form. Electrons are forced into protons, creating neutrons and neutrinos. The outer layers collapse, rebound, and may help launch a supernova. What remains at the center is a compact object carrying more mass than the Sun inside a sphere only a few tens of kilometers across. The name suggests a simple ball made entirely of neutrons. The real structure is layered. Near the surface, gravity is so strong that matter forms a thin atmosphere only a small distance deep. Beneath it lies a solid crust. Atomic nuclei remain there, but they are stripped of their electrons and arranged in a dense crystalline lattice. The electrons move through the lattice as a shared quantum gas rather than belonging to individual atoms. Pressure rises rapidly with depth. The nuclei become increasingly rich in neutrons because high density favors their presence. Farther down, a point is reached where some neutrons are no longer bound inside individual nuclei. They begin to move through the crust as a separate fluid. This region is called neutron drip. The nuclei remain in a lattice, surrounded by electrons and by neutrons that have escaped their nuclear boundaries. The word fluid is only partly familiar here. At the low temperatures inside an old neutron star, many of these neutrons are expected to pair through the nuclear interaction. The paired particles can enter a superfluid state, moving with almost no internal friction. The crust, therefore, combines a rigid crystal with a quantum liquid flowing through it. Near the base of the crust, the nuclei may no longer remain roughly spherical. Competition between nuclear attraction and electric repulsion can stretch them into rods, sheets, and more complicated forms. Physicists sometimes call these structures nuclear pasta because of their shapes. The name is informal, but the phases may influence how heat, magnetic fields, and stress travel through the star. The crust gives way to the core when distinct nuclei finally dissolve. Matter becomes a dense mixture dominated by neutrons, with a smaller number of protons, electrons, and perhaps muons. The neutrons are widely expected to remain superfluid through at least part of this region. The protons may form a superconductor, allowing electric current to move in a collective quantum state. This interior is not a quiet ocean. A rotating neutron superfluid carries motion through quantized vortices, narrow lines around which the fluid circulates. A superconducting proton component may confine magnetic flux into thin tubes. The vortices and flux tubes can interact, pin to structures, release suddenly, and exchange angular momentum with the crust. These interactions may help explain glitches, brief increases in the rotation rate of some pulsars. A pulsar usually slows as it loses rotational energy. During a glitch, part of the interior appears to transfer angular momentum outward, causing the crust to spin slightly faster. The event offers indirect evidence that more than one dynamical component exists inside the star. The deeper core is less certain. Density there may reach several times that found inside an atomic nucleus. Laboratory experiments cannot hold large samples of matter under the same cold, compressed conditions. Theory allows several possibilities. Neutrons and protons may remain the main particles. Hyperons containing strange quarks may appear. Meson condensates may form. At still greater density, quarks may no longer remain confined inside separate nucleons and could enter a new phase of matter. No observation has yet selected one complete picture. The central composition may also differ from star to star. A lower mass neutron star may never reach the pressure required for an exotic phase, while a heavier one may contain a core unlike anything in the outer layers. The problem is summarized through the equation of state. This is the relationship between pressure, density, temperature, and composition. For the cold matter in a mature neutron star, the central question is, how much pressure appears as density rises? A stiff equation of state produces strong pressure and usually supports a larger radius. A soft equation of state allows matter to compress more tightly and tends to produce a smaller star. The existence of neutron stars with masses near twice that of the Sun already places a firm boundary on the theory. Any proposed equation of state that cannot support such a star must be incomplete or wrong. At the same time, the star cannot grow without limit. Beyond a maximum mass set by the equation of state, pressure can no longer balance gravity, and continued collapse produces a black hole. The exact position of that boundary remains uncertain because it depends on the same hidden composition being tested. Mass alone cannot fully reveal the answer. Several equations of state can support stars with similar masses while predicting different radii. Measuring both quantities for the same object narrows the range of possible interiors. NICER was designed for this task. Mounted on the International Space Station, it records X-rays from rapidly rotating neutron stars. Some of these stars have small hot regions on their surfaces, often near magnetic poles. As the star spins, the hot regions move in and out of view, creating pulses. The pulse shape depends on more than rotation. The star's gravity bends light, allowing part of the far side to remain visible. A more compact star bends the light more strongly. Rotation changes the arrival times and energies of the photons. The position, shape, and temperature of the hot regions also affect the signal. Researchers construct models containing these effects and compare them with the observed X-ray pulse profile. The result is not a direct photograph of the surface. It is an inference drawn from the changing light. By the middle of 2025, NICER had produced robust radius measurements for 3 neutron stars, combined in some cases with mass information from radio observations. These measurements do not yet identify one final equation of state. They remove possibilities that predict stars too small, too large, or unable to support the heaviest known neutron stars. Each additional measurement adds another point to the mass-radius relation, the curve that describes how a family of neutron stars should change with mass. Gravitational waves provide a second method. When 2 neutron stars orbit one another, each star raises a tidal deformation in the other. A softer star is easier to compress and distort. A stiffer star resists more strongly. The deformation changes the orbital motion and leaves a small imprint on the gravitational wave signal. GW170817 carried that imprint as 2 neutron stars approached merger. The signal allowed researchers to place the first gravitational wave constraints on neutron star tidal deformability, and therefore on the equation of state. The measurement was not precise enough to reveal the core composition, but it showed that the stars could not be arbitrarily large or easily deformed. X-ray timing and gravitational waves examine the same hidden matter from different directions. NICER watches light leaving a rotating surface. LIGO and Virgo measure changes in spacetime produced as 2 stars pull on each other. One method depends on the bending of X-rays. The other depends on the distortion of the stars before collision. Future observations may connect these approaches more tightly. More radius measurements can trace the mass-radius curve. Additional mergers can improve tidal constraints. A nearby supernova may reveal neutrinos from the formation of a new neutron star. Cooling observations can test how superfluid particles carry and release heat. The interior will remain invisible in the ordinary sense. No telescope can look through the crust and photograph the core. Its structure must be reconstructed from rotation, radiation, cooling, gravity, and sudden changes in motion. The simplest statement is therefore also the most careful. A neutron star is not one immense atomic nucleus, and not a uniform sphere of neutrons. It is a layered quantum object. Its crust is crystalline. Its inner regions likely contain superfluid neutrons and superconducting protons. Its central core may contain forms of matter that have never existed in a terrestrial experiment. At the surface, an X-ray pulse crosses space. In a detector, its arrival time is measured. Far below that light, neutrons pair, vortices turn, magnetic flux threads the core, and pressure holds matter just short of collapse. The star remains whole, carrying its unanswered interior through the dark. The heaviest elements do not form by simply placing one proton after another into a nucleus. Positive charge makes each additional proton harder to add. Beyond iron, ordinary fusion no longer releases the energy that keeps a star supported. Another route is needed, and that route often begins with neutrons. A neutron carries no electric charge. It can approach a positively charged nucleus without facing the same electric barrier as a proton. If the nucleus captures it, the mass number rises by 1, while the element remains unchanged. The new isotope may be stable. It may also contain too many neutrons, and later undergo beta decay, turning one neutron into a proton. The atomic number then rises, and the nucleus becomes the next element in the periodic table. Capture and decay can repeat. A nucleus gains a neutron, waits, changes, and gains another. Over time, this sequence builds elements that fusion alone does not easily reach. In the slow neutron capture process, usually called the S process, captures occur slowly enough that an unstable nucleus often has time to beta decay before another neutron arrives. This process unfolds mainly in evolved stars, especially asymptotic giant branch stars, where nuclear reactions release modest streams of neutrons. The path remains close to the valley of stability. A nucleus captures one neutron, perhaps another, and then pauses while beta decay moves it toward a stable isotope. The sequence produces much of the strontium, barium, lanthanum, and lead found in the universe. Convection carries these nuclei through the star, and stellar winds later return some of them to interstellar space. The rapid neutron capture process follows another path. Here, the neutron density becomes so high that nuclei capture many neutrons before beta decay can keep pace. The path moves far from stability into regions filled with short-lived, neutron-rich isotopes. When the supply of neutrons ends, these nuclei decay back towards stability. Neutrons become protons through the weak interaction. The nuclei move across the periodic table, producing elements such as gold, platinum, thorium, and uranium. For decades, the required environment was known more clearly than the place that provided it. The R process needs an enormous concentration of free neutrons, rapid expansion, and conditions that allow newly formed nuclei to escape before they are broken apart. Core collapse supernovae were considered natural candidates. Some may contribute under particular conditions, but an ordinary supernova does not always produce a sufficiently neutron-rich outflow. Neutron star mergers offered another possibility. Two compact remnants can orbit one another for millions or billions of years while losing energy through gravitational waves. Their separation slowly shrinks. In the final seconds, the stars circle hundreds of times per second, deform under each other's gravity, and meet. Matter torn from them expands into space, carrying more neutrons than any ordinary nucleus could hold. For a short interval, the escaping material remains rich enough for rapid capture. Nuclei absorb neutrons and later decay. The heat released by those radioactive decays powers a transient glow known as a kilonova. On August 17th, 2017, the LIGO and Virgo detectors recorded gravitational waves from such an event. The signal was named GW170817. Less than 2 seconds later, a short gamma-ray burst arrived from the same region of the sky. Telescopes then found a new source of visible and infrared light in the galaxy NGC 4993. This was the first time a neutron-star merger had been observed through gravitational waves and across the electromagnetic spectrum. The gravitational waves traced the orbit and masses of the stars. Gamma rays marked a relativistic outflow. Visible and infrared light followed the expanding debris. The glow changed color over several days. Early light contained a bluer component associated with material having fewer heavy neutron-rich nuclei. Redder light emerged as the ejecta cooled and as elements with complex electron structures absorbed shorter wavelengths. The change matched the behavior expected from radioactive R-process material. A later analysis identified strontium in the expanding debris. Strontium is not among the very heaviest elements, but its detection was a direct chemical signature of freshly produced neutron-capture material in a neutron-star merger. The event showed more than a plausible source. It showed a newly made element in the aftermath. The exact composition of the ejecta remains a subject of modeling. The light depends on the shapes of the debris clouds, their speeds, their neutron richness, and the nuclear properties of isotopes that are difficult to create on Earth. Many of those isotopes have poorly measured decay rates. The color of a kilonova, therefore, contains both an astronomical story and a nuclear physics problem. GW170817 established neutron-star mergers as real R-process factories. It did not prove that they are the only ones. Some heavy elements appear in old stars that formed early in galactic history. Rare types of supernovae or collapsers, the collapse of rapidly rotating massive stars, may also contribute. The origin of gold is therefore not one sentence. Some nuclei may come mainly from mergers. Others may receive contributions from more than one site. The proportions can change with time and environment. What is clear is the role of the neutron. The lack of electric charge lets it enter a nucleus that would repel another proton. Its capture creates unstable isotopes. Its later beta decay changes the identity of the element. The strong interaction binds the enlarged nucleus, while the weak interaction guides it back toward stability. A gold nucleus contains 79 protons. Its stable isotope contains 118 neutrons. Those neutrons are part of the balance that allows the nucleus to exist. The same is true for platinum, lead, thorium, and uranium. Heavy matter is possible because neutrons provide nuclear attraction without adding electric repulsion. After a merger or an enriched stellar wind releases these nuclei, they join the thin material between stars. Some become dust grains or ions in gas. Gravity later gathers that material into new clouds. The cloud that formed the solar system contained hydrogen and helium from the early universe, carbon and oxygen from older stars, S-process elements from aging giants, and R-process material from earlier explosive events. The mixture collapsed around 4.5 billion years ago. Most matter fell toward the young Sunday. A smaller portion settled into a disk and formed planets, asteroids, and smaller bodies. Heavy elements entered the growing Earth. Iron moved toward the core. Other elements remained in the mantle and crust, or arrived later in impacting material. A gold atom in rock may have passed through several environments before reaching Earth. Its nucleus may have formed in neutron-rich ejecta, cooled into dust, crossed interstellar space, entered the solar nebula, and become trapped inside a planet. The nucleus carries no visible record of that journey, only its present structure. Within that structure, the neutrons are stable because the complete nucleus lies in a lower energy state than the available alternatives. Removed from the nucleus, an individual neutron would again become temporary. Bound inside gold, platinum, carbon, oxygen, or iron, it can remain for times longer than any human history. The story that began with a neutral particle in a classroom diagram has crossed several scales. Quarks and gluons create the neutron's mass. The weak interaction allows it to decay. Nuclear binding changes whether that decay can occur. The early universe places neutrons into helium. Stars create new ones slowly. Dying stars and merging remnants use them to build the heavy elements. No single scale contains the whole explanation. The neutron is a quantum-bound state, a nuclear component, a participant in stellar reactions, and a carrier of cosmic chemical history. Each description becomes useful at a different distance. In the quiet matter of the present, those histories overlap. Neutrons remain inside the oxygen of water, the calcium of bone, the iron carried through blood, and the heavier elements scattered through stone. Some of their nuclear arrangements were first assembled in stars that vanished before the sun existed. The particle itself has no memory of those places. It does not know whether it once moved freely through expanding debris or entered its nucleus during a slow capture in an aging star. Still, the structure that holds it is a result of that path. A neutron alone lasts only minutes. A neutron bound in the right nucleus may remain while stars form and fade around it. Between those two states lies the architecture of matter: strong fields, weak transformations, energy valleys, stellar interiors, and the cooling light of distant mergers. The final image is not one of a particle isolated in darkness, but of matter carrying its origins quietly. Inside every stable nucleus, neutrons rest within arrangements shaped by events spread across cosmic time. The motion beneath them continues. The balance holds. The neutron story does not end inside the nucleus or in the debris of distant stars. Its lack of electric charge gives it another role, one that turns the particle into a quiet probe of matter. A charged particle approaching an atom feels the electric fields of the electrons and nucleus long before reaching the interior. A neutron can pass through those outer fields with far less disturbance. It may cross deeply into a material before interacting, carrying information from places that light, electrons, or charged ions do not reach in the same way. This makes neutron beams useful for looking inside matter without taking it apart. In a research reactor or spallation source, neutrons are produced, slowed, shaped into beams, and directed toward a sample. Some pass through, some scatter. The directions and energies of the scattered neutrons contain a record of where atomic nuclei are arranged and how they move. The method resembles diffraction with X-rays, but the two probes respond to different features. X-rays interact mainly with electrons. Heavy atoms, which contain many electrons, often appear strongly, while hydrogen can be difficult to locate. Neutrons interact with atomic nuclei, and the strength of that interaction does not rise smoothly with atomic number. A light nucleus can scatter neutrons strongly. Hydrogen, in particular, often becomes visible in a way that is difficult for X-ray methods. This difference allows neutron diffraction to reveal the positions of hydrogen atoms in crystals, proteins, battery materials, and water-bearing minerals. Hydrogen may be the smallest atom, but its placement can decide how a molecule folds, how a proton moves through a membrane, or how water is held inside stone. A neutron beam can make those hidden positions part of the measured pattern. The neutron's spin adds another layer. Although it has no net electric charge, it has a magnetic moment. When a material contains ordered magnetic moments, polarized neutrons respond to that internal magnetism. Their scattering can reveal how spins align, where magnetic domains form, and how magnetic order changes with temperature or pressure. This is not the same as photographing a tiny bar magnet inside matter. The experiment measures a pattern assembled from many scattering events. From that pattern, the magnetic structure is reconstructed. Antiferromagnets, superconductors, and other materials with complex internal order can be studied in this way. The neutron becomes sensitive not only to where atoms sit, but also to how quantum magnetism is arranged among them. Neutrons can also measure motion. If a neutron loses or gains a small amount of energy while scattering, that change can reveal vibrations in a crystal lattice, rotations of molecules, diffusion of hydrogen, or collective excitations in a magnetic system. The sample is not only a structure frozen in place, it is a field of motion, and neutron spectroscopy listens to that motion through exchanged energy. In this setting, the neutron remains a composite particle of quarks and gluons, yet it behaves as a carefully controlled wave. Its wavelength can be chosen by slowing it to a suitable energy. When that wavelength becomes comparable to distances between atoms, diffraction appears. Peaks form at particular angles, carrying the geometry of the sample into the detector. Some experiments slow neutrons much further. Cold neutrons move more gently than those produced in high-energy reactions. Ultra-cold neutrons move more slowly still, with energies so low that gravity becomes a useful laboratory force. They can be reflected from certain material surfaces, confined by magnetic fields, and stored for hundreds of seconds. At such low energies, the neutron's vertical motion above a mirror can occupy discrete quantum states. Gravity pulls downward. The mirror provides a boundary. Between them, the neutron forms standing wave patterns with allowed heights measured in micrometers. The system is sometimes described as a quantum bouncer. These measurements test quantum mechanics in a regime far removed from electrons in atoms. They also search for tiny deviations from ordinary gravity at short distances. No confirmed departure has appeared, but the neutron provides a clean way to look because its electric neutrality reduces many background forces that would complicate a charged particle. The neutron's neutrality also makes it a useful subject in searches for a permanent electric dipole moment. An electric dipole moment would mean that positive and negative charge are separated slightly within the particle. The neutron has an internal charge distribution, but a permanent dipole aligned with its spin would carry a deeper meaning. It would signal a violation of symmetries, that the known strong interaction appears to respect far more closely than simple theory might suggest. Experiments place ultra-cold neutrons in carefully controlled electric and magnetic fields. The neutron spin precesses, turning slowly around the direction of the magnetic field. If a permanent electric dipole exists, reversing the electric field should change that precession by a tiny amount. The task is to distinguish such a shift from magnetic drift, field gradients, leakage currents, mechanical motion, and every other influence that can imitate the signal. No permanent neutron electric dipole moment has been detected. The upper limits are extraordinarily small. The absence itself is important because quantum chromodynamics contains a possible symmetry-violating term that could make the dipole much larger than observed. The fact that nature seems to suppress this effect is known as the strong CP problem. One proposed solution introduces a new particle called the axion. In that picture, a new field naturally drives the offending parameter toward a value that keeps the neutron's electric dipole extremely small. Actions have not been confirmed. They are also candidates for part of the dark matter that shapes galaxies through gravity, while remaining unseen in ordinary light. Another unanswered question concerns the difference between matter and antimatter. The laws of known particle physics allow some violations of charge and parity symmetry, usually called CP violation. These effects are real, but the amount contained in the standard model appears too small to explain why the observable universe contains far more matter than antimatter. Neutron decay offers a low-energy place to test that framework. The directions of the emitted electron, antineutrino, and proton can be compared with the neutron's spin. Their correlations depend on the structure of the weak interaction. Precise measurements search for small deviations from the expected pattern, including interactions that would not fit the usual left-handed form of the weak force. Most results agree with the standard model. That agreement narrows the room for new physics. A tiny discrepancy, if repeated across independent experiments, could point toward heavier particles or additional interactions that cannot be produced directly at present energies. The neutron becomes a laboratory where high-energy ideas leave low-energy traces. There is also the possibility that a neutron could transform into an antineutron. An antineutron has the same mass and no net electric charge, but its internal quarks are replaced by antiquarks. Such a transformation would violate baryon number, the bookkeeping rule that distinguishes matter particles like protons and neutrons from their antimatter partners. No neutron-antineutron oscillation has been observed. Experiments have searched using free neutron beams and through the stability of nuclei. If the process exists, it must be extremely rare. Even so, the search continues because baryon number violation could help explain how the early universe developed its excess of matter. A free neutron is especially valuable in this search because it is not surrounded by the complex energy environment of a nucleus. Magnetic fields must be reduced to very low levels, since even a small difference in energy between neutron and antineutron states can suppress the oscillation. A long flight path gives the neutron more time to change before reaching a target where an antineutron would annihilate. The expected signal would not be a single quiet particle. An antineutron striking ordinary matter would annihilate with a nucleon and produce several mesons. Detectors would look for the characteristic burst and reconstruct whether it came from the end of the neutron flight region. The neutron also tests gravity itself. Because it has no charge, it avoids many electrical forces that overwhelm gravity for elementary particles. Experiments have observed neutrons falling under Earth's gravitational field, forming quantum states above mirrors, and accumulating phase shifts in neutron interferometers placed at different heights. In an interferometer, a neutron wave is split along two paths and later recombined. If one path sits higher in Earth's gravitational field, the phase evolves differently. When the paths meet, the interference pattern shifts. The experiment shows gravity acting directly on a quantum matter wave. A neutron's passage through matter can also reveal the slow movement of water, stress inside metal, and changes occurring within working machines. Neutron imaging is used to study fuel cells, engines, batteries, archaeological objects, and biological materials. Because many metals are relatively transparent to neutrons, while hydrogen-rich substances scatter or absorb them strongly, water and oil can be seen inside metal housings. A running component can therefore be examined without opening it. Fluid moves through channels hidden by steel. Lithium shifts inside a battery during charging. Moisture enters a porous material. The neutron carries these internal changes outward as variations in transmission. This practical work belongs to the same physics as the deeper questions. The particle's neutrality lets it penetrate. Its magnetic moment makes it respond to spin order. Its wave nature produces interference. Its beta decay tests the weak interaction. Its possible electric dipole tests symmetry. Its possible transformation into an antineutron tests the stability of matter itself. The neutron seems quiet because it carries no net charge. That quietness is what makes it useful. It can enter places where charged probes are turned aside. It can remain long enough to be stored, reflected, polarized, and timed. It can reveal matter without bringing much electric disturbance of its own. Each experiment chooses one part of the neutron's identity. A diffraction instrument uses its wavelength. A magnetic scattering experiment uses its spin and magnetic moment. A lifetime experiment uses its decay. A gravitational trap uses its mass. A symmetry test uses the detailed structure of its interactions. The particle has no single role. It is material and messenger at once. There is a gentle symmetry in that. The neutron is difficult to see directly, yet it helps make hidden structures visible. It is unstable when free, yet its brief freedom allows some of the cleanest tests of physical law. It carries no total electric charge, yet its internal charges may hold clues about forces and symmetries not fully understood. The unanswered questions do not diminish what is known. They show where the description remains open. The strong interaction explains confinement and most of the neutron's mass. The weak interaction explains beta decay. Nuclear binding explains stability in matter. Cosmology and stellar physics explain where neutrons become part of larger structures. Still, the exact free lifetime is not settled between methods. No electric dipole has appeared. No neutron-anti-neutron oscillation has been seen. The full distribution of spin and momentum among quarks and gluons continues to be refined. The densest neutron-rich matter remains hidden inside stars. The neutron, therefore, stands at a boundary between established theory and careful uncertainty. It is familiar enough to sit in every basic drawing of an atom, but deep enough to connect particle physics, materials, science, gravity, astrophysics, and cosmology. A beam crosses a crystal and returns a pattern. An ultra-cold neutron rises a few micrometers above a mirror. A trapped spin turns slowly in a magnetic field. A distant neutron star bends X-rays around its surface. The settings are different, but the same particle moves through all of them. After so many scales, the story can begin to quiet. The neutron has been followed from quarks to nuclei, from the first minutes of the universe to stellar remnants, from heavy elements to laboratory mirrors. Nothing further needs to be added for the structure to hold. The remaining movement belongs to the experiment still running and the stars still turning. The particle continues its work without noise, inside matter, and across the instruments built to understand it. The final return can now be slow. The experiments can fade into the distance now. The beams, mirrors, magnetic fields, and quiet detectors can continue without attention. Their measurements belong to another hour. The neutron remains inside the matter of the room, hidden within nuclei that do not need to be seen in order to hold. The fields inside it continue their motion. The quarks remain confined. The balance stays where it is. Nothing needs to be followed any farther. The room can return slowly, not as an interruption, but as the final part of the same journey. The weight of the blanket, the stillness of the air, the surface beneath the body, all of it is made from particles carrying histories older than the Sunday. Those histories can rest without explanation. Breathing may settle into a softer rhythm. The muscles around the eyes can loosen. The hands can remain still. Any sound in the distance can pass without being named. Beyond the walls, Earth turns beneath the night. Farther out, stars continue their slow changes. Some are forming from cold clouds. Some are shining steadily. Some have already released their matter into space. None of them need to be watched. Inside every stable nucleus, neutrons remain held within arrangements that have no lower place to go. Their hidden movement continues beneath the calm surface of things. The journey ends without closing the universe behind it. The measurements continue. The stars continue. Matter keeps its quiet structure. For now, there is only the darkened room, the steady weight of the body, and the slow fading of thought. The last image can be simple. A single neutron resting inside a nucleus, not alone, not changing, held in balance while everything around it grows quiet, is greater than, is greater than, is greater than. End of script. Sleep well.